we will try to establish in the end a connection between a differential equation. Here, we will talk about essentially differential mixed equations, difference and differential equations. The applications of the mixed equations are huge. We can find several applications in economy, biology, physics, medicine, a lot of things, a lot of places. For example, here we have one paper about a cancer model where we have mixed type equations. Here we have another one, macrodynamic models with policy lag in stability, instability, etc. Another one, application in production systems, so industry use the mixed equations too. Here we have another one with applications in economy. Here, economic dynamics, the name says everything. Once more, economy. So we can find in the literature several cases. And why is this kind of equation so important? These kind of equations are very important because it establishes a relationship between past and potential future events. And when we know the past and when we know what we want for the future, we are able to make a good decision. And is this what our equations bring us when the equation is over mixed factors? Of course, that this kind of equation is a challenge. And why it is a challenge? It is a challenge because it's very difficult to formulate an initial value problem for this kind of equation to guarantee the existence and uniqueness of solution. So several times we start a work saying, okay, we suppose that the solution exists. Of course, that after we will work with the application, with the examples, we will find several cases where the solution exists and is unique. However, when we start, we must be very careful. Several mathematicians are working on this problem. Sometimes we can establish some conditions. However, it's not so clear as when we have the delay equation. For delay equation, we can be sure about the uniqueness and the existence. Here is more difficult, and it's a very sensitive case. However, it's a kind of equation very interesting. So part of this work, we will talk about the oscillatory behavior of this equation. What we have here? Here, we will have the delay term, where this delay term is positive, is less or equal to n minus 1, so less than n, and the limit is infinity. On this side, we have the advanced term. The advanced term must be more than n, so it can be equal or more than n plus 1. And of course, it goes to infinity and must be positive too. P and T, here the coefficients are real functions. Several of the results that we will find here, it was developed by a paper with my two co-authors, the Professor Nerjan Kandani and Professor Ali Fuat. Ali, I know that he is here listening, so it was a surprise for him to see some of his results here. So, second part of this work, we will talk, or we will see only a few results and the comparison between our equation and the differential equation. Here, just like before, we will have the delay part, where the delay is positive, less than t, and going to infinity, just like before. Here, we have the advanced term, and the advanced term must be more than T, positive of course, going to plus infinity of course. It is evident from here. And P and T are real functions. Sometimes our temptation is to say, okay, the equations are very similar, we can work with them in similar. The answer to this is yes and it's no. Who works with both equations knows how it is sometimes to establish a connection between these two equations, but knows too how it's hard to do it in some cases. This it will be the last part of the talk. Now we will talk about the difference equation. So, difference equation, the qualitative theory about this equation drawn considerable attention from several mathematicians. Here we have a good example with this book from Agadval, from LA, An Introduction to Difference Equation. Here, Kelly and Peterson, well, Frigianti and Lerner-Scatten, several mathematicians work with. Several of you work with it. So, this equation that we have here is a particular case that the equation that we saw before. It was introduced on this paper, Oscillatory Mixed Difference System, in 2006. And it was published the oscillatory criteria for the oscillatory behavior of this equation. This work, it was concerned with behavior of solutions of autonomous linear mixed type difference equation, and the result, it was obtained using the characteristic equation. This one, it was introduced in 2016 on this paper, Oscillatory Properties for a Scalar Linear Difference Equation of Mixed Types. And later in 2018, asymptotic behavior of a scalar linear difference equation of mixed equation. More. Here, when we consider only the delay part, or when we consider that the coefficients of the advanced part are removed, we can see several results in the literature. Here we have some examples. For example, here in this paper, asymptotic behavior of a linear delay difference equation, or in this, the limits of solution of a non-autonomous linear delay difference equation. More, an asymptotic result and stability criterion for linear non-autonomous delay difference equation, or in this one. Well, we can spend here a lot of time finding results just for the delay part. What we can do when we have, well, a particular case of the equation is this one. As we saw before, here we have the coefficients, variable coefficients are sequences. Here the coefficients are numbers, are 6 numbers. And this one, it was developed in the oscillatory mixed difference system too, as we saw before. And here, more recently, 2 years ago, with my dear author, co-author, Professor Alice Roy, and Yulin Yang. So, when is an equation non-oscillatory? Well, an equation is non-oscillatory, or a solution is non-oscillatory when it is eventually positive or eventually negative. If all otherwise is oscillatory, we will say that equation is oscillatory when all solutions are oscillatory. However, one non-oscillatory solution is enough to say that our equation is non-oscillatory. So let us see what we have. We will consider C and T, non-negative sequences, where this limit is more than 1. So this is enough to guarantee that our equation is oscillatory. In the other words, all solutions oscillate. What is this sigma? Well, this sigma is the minimum of the advances, tau is the minimum of the delays, and T is the sum of all coefficients of the advanced part. It's the sum of all these coefficients. So you can see here that the advanced part is very strong for this condition. Only this sum is important for us, not the delay, the coefficient of the delay. The proof, here is just a graph of the proof. We will consider that there exists a non-oscillatory solution. So, when we take our equation, we obtain that the x is an increasing solution. So, if x is an increasing solution, when I do the sum in both sides of our equation, a sum between tau and sigma minus 1, we obtain this. Rearranging all the terms, what we will obtain? We obtain that this is negative. Well, but remember that P is positive, plus 1 is positive, the solution is positive, and here is, by our assumption, is positive. So it's not possible to obtain here something negative. Yes, this is a contradiction. If it is a contradiction, it means that our solution is oscillatory. Now, particularly, we will establish a similar result for particular case, where we have the delays as n minus sigma or n plus tau, tau and sigma. Let us see an example. Here, we will consider C1 as E over Ln of 4. Here, it is the coefficient of the advances part. Here, the delays are not important. Coefficients of delays are not important, only this one. And here it is the delay and the advance. So, what is tau? Tau is n minus 2 sigma n squared plus 1. And the question is the sum of these two results more than 1? Well, what we want to know is this more than 1? Let us see. Here it is. Well, when we take this sum, this is more than this result. Using why? Because we can use so well-known theorem that we use this several times. So we establish this value. Well, using exactly the same, we can see that exactly the same sum is less than this. Well, but what is the limit? The limit that I have here is the same limit that I have here. It has exactly the same limit. And the limit is E over 2. And this is more than 1. So, our limit is more than 1. And by first theorem, all solutions of our equation oscillate. So, we have an oscillatory equation. Now, taking again our theorem, we will make here a little change. What we will change here? We will establish a second theorem, and we will replace here. I will have the limit superior of t more than 1 between tau and sigma, and now I replace by the limit superior between n and sigma j minus 1 of this C more than 1 over E. So what we did get this new theorem? Well, first step, it was considered this sequence, CJN. From here, easily we can prove that CJN is between 1 over 4 and 1 over E. This limit more than 1 over E. So, what this means? It means that this sum is more than 1 over E plus something, epsilon 0. Taking these two inequalities, we can be sure that our sum between the sum of the coefficients between T and Cj is what? Is more than 1, is more than something more than 1. And the secret of this secret is between commas, is the main point of this theorem. So, we will consider, just like before, that x is positive, so xn is increasing, and if it is increasing, we have these two inequalities. When we use these inequalities, what we will use these inequalities in our equation, what we will obtain? We will obtain, first, dividing the equation in both sides, of course, by xn plus 1. By one side, we will get these coefficients equal to the product of this, easy, but using the inequality, we have that this is less than 1 minus 2. Using the inequality of arithmetic and geometric means, what we will get this. And here we have something much more complex. And it is here that is important what we talked before. But before of that, we use these inequalities for each one between 0 and 1. And here we can see that this verifies this condition. And so what we get? We will get that the x of sigma dividing by xn is more than 6. Here is the C, almost the C that we saw before. So, using here our inequality that we thought that is more than D, and repeating the process once, twice, etc., 3 times, what we will get? We will get that this inequality is more than the C. But by the other hand, we keep this on our mind, and by the other hand, when I divide xn by xn plus 1, now it's different that we did before, we obtain this inequality. And from here, we will have that x of sigma dividing by xn multiplied by t is less than 1. Well, I can consider the sequence going south, theta, going to plus infinity. And when I do this coefficient, I will obtain something like 1 over c. And this is the finite number. So, this limit exists. Well, attention, because we saw that this coefficient is more than the c, and d is more than 1. So, this limit is infinity. And it's from here that we obtain a contradiction between this and this. Exists, don't exist. Contradiction, so all solutions are oscillatory. The corollary is very similar to the theorem, but here is for this particular case. Let us see the example. Here, the coefficients are constant. We have the delay, we have the advances, and here it is first delay, the first advance, second advance, and the question. Is this more than 1 over e? In the other words, is this more than 1 over e? Yes, it is. It is here. Is this more than 1 over z? Yes, it is. Because I must do it for sigma 1 and sigma 2. So I have to limit to this. So, using second theorem, all solutions of our equation for sure. First theorem is very similar with first one, but here T and T are non-positive sequence. So when the T and T is non-positive, I will work with the delay, not with the time. Here once more we have sigma has the minimum of sigma I. Here tau is the minimum of the delay, here the advances, and T is the sum of all coefficients of the delay part. The proof is very similar, so I pass to the corollary. The corollary is an adaptation, in fact, for this particular case. And the example. Here, C2 is 3 over 2 logarithms of 2. Here is the entire part of 0.5 n and of n 0.5. So we have 2 delays, we have 2 advances. Tau is the entire part of 0.5 n. Sigma is n plus 1. And the big question, is this less than minus 1? Or developing, doing some calculus, we obtain this sum. Is this less than minus 1? Yes. We can do like before to establish a comparison. Okay. Here it is this limit is equal to this one. So this the limit of our sum, it will be minus 3 over 2, and this is less than 1. So all solutions of our equation to show. What can we change here in first theorem to establish the new one? Well, is to replace that condition by this one, just like we did in between first and second theorem. We can do it for first and first theorem. The proof is similar, the main idea is similar, so I don't bring you the proof. The corollary is the particular case. And the example. Here, once more, the coefficients are constant. Here, we have the delays, we have the advances, both delays, and the question, is this less than minus 1 over e? First limit, yes, it is. The second one, yes, it is. So, by first theorem, all solutions of our equation are selected. So, let us now to consider the particular case of the difference equation with constant coefficients. This is the part developed by our colleague, Professor Ali. It's about stability. So, unfortunately, until now it was not possible to establish the conditions for stability when we have variable coefficients, and is the reason because we must bring constant coefficients. So C and C are real numbers, L and M positive integers. Here we have the powers of words. So the characteristic equation is given, as we know, by this equation. And the main point to establish the stability of an equation is this property. This property is in the basis of the problem. So I'm trying to do this fast because I take a lot of time in the beginning and I don't want to push you too much. So let us consider lambda 0, a positive real root of the characteristic equation with the property A. And we will have beta of lambda 0 as this expression. So for any initial condition, we will have. Your question is, we know what is beta, it's here. We know what is lambda 0, it's here, but what is this L? Well, the L is this. It's this big expression. It's the relationship between the initial condition with our equation. And here it is, what is L? It will appear later. So let us suppose some property A, here it is, the property mu is less than 1. And we know that the modulus of beta lambda 0 is less than this. So when we use the property A here, what we will have? We will have that modulus of beta of lambda 0 is less than 1. Or in the other words, 1 plus beta 0, it will be more than 2. So we can be sure of this. So we will take the expression of our equation and we will do a change of variable. In the other words, we will do epsilon n as lambda 0 of n minus 1 multiplied by n. When I replace this on this expression, what I will have? I will have that this is equal to this one. Just to replace it. So, after a couple of steps, we will, and knowing that lambda 0 is a positive real root of our characteristic equation, we obtain this. Lambda 0 n, and here it is our expression completely blocked using the positive real root of our characteristic equation. So, from our equation, what we will have? We will have a new equation. Depending of epsilon n. And these two equations are equivalent. In fact, it's born from a change of variable. So if I have an initial condition for x, I will have an initial condition for n, for epsilon. And here it is the initial condition. What's doing this job? So epsilon n, it will be rewriting on this form. And here it is the L, just like we defined before. It's just a graph. New change of variable. Dn is equal to n minus L lambda 0 c dividing by 1 plus b. This is positive, remember? So b can be expressed on this form using exponent. We can change the variable and establish condition of b. And if epsilon n works with initial conditions, Dn will work with the initial condition too. So the question is, the limit of Dn is 0, because what I want to prove is if this here is positive. So let us see. We will define M as this, the supreme of this difference. So this, if it is defined this way, so the modulus is less or equal to S. Step by step, we reach this inequality. The norm of D is less than this expression. But this is mu, and mu is less than 1. So what we will have, computing several times, we can have this, and in fact, by property A, we know that mu of lambda 0 is less than 1. What we obtain the limit is just like this. Now, lambda 0 is a positive real root of the characteristic equation with property A, just like before. Beta is just like before. So, for any initial condition, we get this inequality. From here, what is n? This n is this expression, is this function, depending by the root of characteristic equation. And from here, this k, what is this k? This k is lambda 0, k of lambda 0 is the maximum between these two values. L is the limit superior of sum and n. So, more. We can say that this solution of the mixed difference equation is uniformly stable for lambda 0 more equal to 1, uniformly asymptotical stable for lambda 0 less than 1, and unstable for lambda 0 more than 1. Let us see the proof. Well, L, we know we worked with this before, and it is given by this expression. From here, when you apply the modulus, what we obtain that modulus L is less than this. And after a couple of steps, using the maximum between lambda 0 and lambda 0 E here, what we will get, and knowing that this is less than kappa of lambda 0, and this one less than kappa of lambda 0, we will get this. So, what is, we know, we saw this before, property A again. So what we have here is that the modulus of L is less or equal to the norm of the initial condition multiplied by 1 plus mu kappa in 1 plus. So, taking now the M and doing a couple of steps, what we obtain? We obtain that M is less than kappa plus this coefficient multiplied by the norm of phi. So, using the same epsilon that we used before, easily we can find, easily is not so easily, however, the modulus of epsilon n is less than n of lambda 0 phi. So, what we have? We will have that x, it will be less in modulus, of course, less or equal to this expression. But just for your attention here, it's from here, from this inequality, that we can establish the stability, because if lambda 0 is 1, it's easy to understand that we have a stable solution. For lambda 0 less than 1, when we do the limit, we have the asymptotic stability. And for lambda 0 more than 1, of course, that we will have an unstable solution. So, from the lemma, I like particularly of this one. In fact, I think that it's very nice and very easy to be applied. We will establish some inequalities. This one, what we have between first and second one. Well, here we have sum, here we have difference, r plus 1, here is just r, and here we have inverse of this value. And third inequality is given by. So, in this interval, r plus 1 divided by r, and here r divided by r plus 1, here it is. Characteristic equation has a unique positive root, and this root satisfies property A. Let us see how it was proved. We will define the function f. Well, when I do the f in r divided by r plus 1, I obtain this. And I can be sure, using the first assumption, I can be sure that this is positive, is negative. And here, because here everything is positive, here everything is negative, so this is negative. And when I do it in the upper limit of the interval, what I will have, this is positive. Well, this is negative, this is positive. So a root we find, because it jumps from positive to negative. In this case, from negative to positive. But it is unique. We will use the derivative function. When we do the derivative of f, what we obtain this. And this is positive by our assumption. So our function is increasing. So it starts in negative, increases until positive. So the root exists and is unique. It is our first assumption. F increases. So f of lambda 0 equals to 0 has a unique solution. It's this interval. It's a very elegant theorem. In fact, it's a lemma. How it was established this further? Well, we will take our new this expression, this mu that comes from the property A, and a couple of steps. Developing this, we obtain that this is less than 1. Why? Because we assume that it's less than 1 in our assumption. So, let us see the corollary. We will have same assumptions, and from here, what we will have asymptotically stable if this sum is less than 1, and unstable when it's more less than 0, and here more than 0. So it's, in fact, this lemma and this corollary are very easy to be used. The proof is very elegant. The other is nice too, but much more complex. But from there, we can establish something very easy to be used. So let us see first example. Here it is our equation, delayed and advanced first, characteristic equation, and look. When you look to the characteristic equation, what we will have? We have four roots. Two roots, real roots, two imaginary roots. So this is the root that we reach. Lambda 1 equals 2. So by the theorem 2, the solution is uniformly stable. Here, for the second example, delayed and advanced fast characteristic equation, we have lambda 1 and lambda 2. Here, both are positive. Well, how can I choose? This one verifies the property A, so forget this one. This one verifies the property A. So, by the second theorem, the solution is uniformly asymptotically stable. In fact, if you wish to use the corollary, you can do it. Very easy because R is 1. So, when we do this sum, what we obtain? A negative value. So, by the corollary, the solution is uniformly asymptotically stable. Now, how can we establish a connection between differential and difference equations? Of course, that mathematicians give a big contribution to the study of differential equations, like the other one gives to the difference equation. Here we have some examples. Berazanti, Christine, Agarwal, Giori and Ladas. This is a big contribution on this field. I think that everyone that works with delayed differential equations has this book involved. Here, another one. Well, the contributions are huge, and some of you did it too. So, we recall the equation that we saw just in the beginning. And now, when I recall my first theorem, it was this one with non-negative sequences, and here the difference equation. Can I establish a relationship between this theorem for the difference equations with the new one for differential equations? I can establish. The proof is very, very similar. What will change? Well, here I will have non-negative function, of course, and here I will have the limit superior not the sum but the integral. And steps of the proof are the same. And here it is, the first theorem for the differential equation. Now I will recall the first theorem. In the first theorem, it happens the same. The proof is very, very similar. I can follow all steps and I obtain a very similar result, not with sum, but with the integral. This is normal. And here it is the result for the differential equation. Very similar with that. So now everything seems to be easy. Everything seems to be nice to jump between one equation and another one. No, that is not true. Why? Because when I recall the second theorem, I will have a problem. And the problem is in the proof. When here I do this division, this coefficient in delay in the difference equation, I can do it here, but I will not find anything. So it's a big difference. For me, it's very nice to work with difference equation and differential equation and to compare results between one another one. However, when I find this kind of problem, it's a big problem. What I can do now? Can I do it? I don't know. I don't have that result yet. So With this, I thank you for your attention, and I hope to meet you one day in Lisbon. Thank you very much.
Thank you very much.